Afternoon, everyone. Sorry I couldn't be there in person, but this is a nice, bright, early start to the day for me. So I'm going to be telling you about a few things that have been happening in my group in association with DataWave over the last, I guess, year and a half or so. But here's some very pretty pictures of cloud formations associated with gravity waves off the coast of Africa to begin with. Here's a bit of an outline. I'm going to be telling you about a machine learning gravity wave parameterization, and then progress to tell you a little bit about calibration and uncertainty quantification. So to develop sort of systematic methods to do calibration and uncertainty quantification associated with gravity wave parameterizations. And I'll also show you a glimpse of some pretty new results from observations from these Loon balloons. Thousands of balloon flights in the upper troposphere / lower stratosphere. But to begin with, it's just a bit of an introduction on atmospheric gravity waves. So gravity waves or buoyancy waves are really quite ubiquitous in the Earth's atmosphere. They're forced by a whole lot of processes, including flow over orography, moist convection, eddy-eddy interactions, jets and fronts, and so on. And once they're forced, they propagate both in the vertical and in the horizontal. And at some point in the atmosphere, a little higher up in the atmosphere, they break and they deposit their momentum. And so they form a forcing on the mean flow. So they either slow down or accelerate the mean flow. They're a really nice example of the multi-scale nature of geophysical fluid dynamics because they have length scales that can vary from 1 kilometer to planetary length scales, so that's spanning about 5 orders of magnitude. And they also have a huge variation in their frequencies. I'm showing you some examples of some pretty small scale gravity waves here at the equator. This is from ECMWF winds. This is sort of in the lower stratosphere. These are Hofmüller diagrams. So you can see that there's some pretty small scale variations in U and V here at the equator. Despite the fact that they have some pretty small wavelengths sometimes at some pretty high frequencies, they are really crucial in atmospheric dynamics. We think that they form a not insubstantial fraction of the momentum budget of the jet stream. We think that they form about a third of the forcing associated with polar vortex breakdown. So the final warming in the southern hemisphere, where we think that models don't have the right gravity wave forcing, and also SSWs in the northern hemisphere. They're really crucial in setting up the QBO and the SAO in the tropics, and we think that they're also important in threshold behavior such as cloud formation, so polar stratospheric clouds, cirrus clouds, and so on. It's just a bit of an introduction. So gravity waves, I mean, some of the gravity waves cannot be explicitly resolved in a typical, let's say 50 by 50 kilometer grid box of a climate model. And so they basically slip through the cracks and have to be parameterized, which is a fancy way of saying that there is, in essence, a black box that tells you what the gravity waves are doing to the mean flow in terms of variables that the model can resolve, such as wind and temperature and geopotential height and things like that. And they're a huge source of uncertainty in climate projection. The current generation of climate models pretty much only permit vertical propagation of gravity waves, which is kind of a problem because there are all of these, for instance, islands in the Pacific, the effect of which are felt thousands of kilometers downstream, and models don't permit this horizontal propagation of these gravity waves. Most gravity wave parameterizations are not observationally validated, and they depend on under-resolved sources such as convection, which is itself parameterized. So this is a bit of a challenging problem, and at DataWave, we are attempting to tackle it from a whole variety of fronts, 3 of which I will tell you about today. But before I jump into that, here's just how bad the situation is. This is from the Canadian climate model, but any other model would probably be kind of equivalent, and I don't mean to say anything about that model specifically, but what we're looking at here is the sea level pressure response to a double CO2 forcing from 2 gravity wave parameterizations in this model that are kind of equivalent. They're equally defensible. There's no way to say from observations whether one is better than the other. And the 2 figures on the left and the center are from these 2 different settings of the model. And the right panel here is the difference between the two. So you can see that in something as basic as sea level pressure, both the sign and the magnitude of the change are quite different, just based on these different parameter settings in the gravity wave parameterization. So today I'm going to introduce three things. The first is a completely data-driven or a machine learning gravity wave parameterization, which we've coupled back into a climate model, and it seems to be accurate and stable, which is pretty nice. It also shows some encouraging signs of being generalizable. In the second part of my talk, I'll tell you about calibration and uncertainty quantification. So assuming that we will always have gravity wave parameterizations, how do we decide how to assign sort of PDFs to these parameter distributions rather than a single value that is manually calibrated, and also sort of carry through these uncertainties in our climate projection. And then I'll tell you sort of at the end about momentum fluxes from these, estimates of momentum fluxes from Loon balloon. Just stop me if you have a question at any point. But stating that, I'm going to jump into the first part of my talk, which is an attempt to come up with a completely data-driven or a machine learning gravity wave parameterization. The hope is, of course, that the ML GWP will at some point be trained on something that resolves gravity waves, observations, or very high resolution simulations. But as a start, we're going to attempt to come up with a gravity wave parameterization which does as well as a conventional and very popular physics-based or a conventional gravity wave parameterization. For this, we are going to be using a model that I'm going to call MIMA. So it's the model of an idealized moist atmosphere. It's based on the GFTL model. It's got the full dynamics. It's also got interactive water vapor and RRTM radiation scheme. And importantly, it has implemented within it a gravity wave parameterization, Alexander and Dunkerton. This is a very popular gravity wave parameterization. And what it does is that it mimics the time and space averaged effect of many discrete intermittent gravity wave packets. So basically, it just adds on a drag to the momentum equation. So it just gives you a drag along the X and the Y direction. It is indeed single column, but this is a first attempt at doing this. So we're going to start with a single column parameterization. As the model architecture, this is a neural network, and we are giving it everything that we can possibly think of, at least to begin with. So we are giving it zonal wind, meridional wind, vertical wind. This model has 40 levels in the vertical, so we're giving it everything. Temperature, geopotential height, latitude, longitude, and surface level pressure. And what the neural network does is that it basically gives us along the vertical column, the drag along the zonal direction and the drag along the meridional direction. The total trainable parameters listed here is rather large. But in this paper, Zach, my student, has done some analysis, and we get pretty good results with about 500,000 parameters or so. So just to jump into exactly how well this is doing, so our neural network parameterization, we are going to call it WaveNet. We thought it was a nice name. So what we're looking at here on top is the gravity wave drag along the zonal direction and along the meridional direction at the bottom. We've got WaveNet on the left, 8099, so the Alexander and Dunkerton GWP on the right, and the center panel shows you the difference between the two. I'm showing you an animation because it's kind of nice to look at, but then we've also looked at things like R squared and so on. So WaveNet is doing actually a pretty good job. And the takeaway here is that the differences between 8099 and WaveNet are actually rather small. We have, to begin with, trained WaveNet on only 1 year of output from the 8099 gravity wave parameterization. And it's interesting in that it seems to be somewhat generalizable. What I'm showing you here is the gravity wave tendency is the drag in the QBO region. So the QBO is, we think, a phenomenon that is driven by gravity waves. So what we're looking at here is from 8099 at the top and from the WaveNet at the bottom. So this has only been trained on 1 year of output from MIMA and 8099, which means that WaveNet has only seen one phase of the QBO, the westerly phase of the QBO. So it's kind of nice that WaveNet is able to both initialize the easterly phase of the QBO as well as reinitialize another cycle of the oscillation. So that's kind of nice. I have highlighted places where WaveNet seems to be overdoing the drag a little bit, but I think that this is fixable with a different, with showing it more data perhaps from WaveNet, from 8099 and MIMA. We've also done quite a bit of analysis that I will perhaps spare you the details, but there's quite a bit of detail in the paper. And we've also tried to do things with Zach-Hall feature experiments in which we gave WaveNet different combinations of input parameters. And what I'm showing you here is the R squared from these different parameters. For instance, the green here is when we give WaveNet all of the variables indicated there. And the red over here is just giving it zonal mean zonal winds, and then the purple is just giving it meridional winds. The takeaway from all of this is that we've also done some Shapley value coefficient of determination calculations. And the point here is that all that WaveNet really seems to need to give us an accurate value of drag is the, for the zonal drag, it needs the zonal wind above and below the level of importance. And for the meridional drag, all it really needs to get a reasonable estimation is the V wind above and below the level of interest. And the Shapley values also shows us that this is kind of consistent with the dispersion relationships for gravity waves, so that's kind of nice. So we've also taken WaveNet and coupled it to MIMA. We've been talking quite a bit to Simon about exactly how to do this, but this was before we were speaking to Simon. So we use 4Pi, which is this interoperability package. What I'm showing you here is, again, the QBO. This is in the equatorial region, 5 south to 5 north. And we are looking at winds in the QBO region with 8099 on top and WaveNet at the bottom. And you can see that it's kind of nice that WaveNet, there have been many such attempts to do a convection parameterization, etc., and then it sort of falls apart. But it seems like this is fairly accurate and stable. So we've run hundreds of years of integration with MIMA coupled with WaveNet. And it does spontaneously generate a QBO, which is nice. The period of the QBO is fairly consistent. So within the within the internal variability of the QBO when run with 8099. However, WaveNet seems to overemphasize the westerly amplitude of the QBO. It's much too large compared with 8099. And I think, again, this is a problem with training, and it can be fixed by training it somewhat differently. The last thing that I'll show you from this piece of work is a quadruple CO2 integration. So I told you that WaveNet was kind of generalizable, and in order for that to be actually true, we need to make it function in a climate that it's never seen. So that's what this is. I don't know how I'm doing on time, but let's focus on basically the bottom. The bottom panels are showing you the climate change response. So the change in the circulation, the zonal mean, zonal winds. In the case of 8099, so a MIMA coupled to 8099, and on the right is a MIMA coupled to WaveNet. So the nice thing here is that the qualitative features of climate change that we think may be influenced by gravity waves are sort of captured by WaveNet in the quadruple CO2 integration. So we do see sort of this forward shifting of the jets in both hemispheres, and also sort of an intensification of the polar vortex. However, with 8099, it seems to be sort of a more barotropic strengthening of the polar vortex in the northern hemisphere, pretty much through the depth of the stratosphere, which is sort of a little underdone with WaveNet. There is a strengthening of the polar vortex, but then it's a bit weaker with WaveNet than with 8099. So, but we think this is a promising start in that WaveNet is able to do about as well as 8099. Note here that this is not saying anything about the response of the QBO or the jets or anything to climate change. WaveNet is just doing whatever 8099 would do. But of course, the next step is to train something like WaveNet on something that actually does resolve gravity waves. And I'll show you a little bit of that maybe at the end of the talk. But this is a good sign in that WaveNet is able to do about as well as 8099, and it seems to generalize to climates that it's not seen, at least qualitatively. The paper is out in GRL earlier this year. All right, I'm going to move on to the second part of my talk, which is saying that assuming that people will always have gravity wave parameterizations, there are parameters in these gravity wave parameterizations which have to be assigned a value. It seems like much of this calibration has been done manually, and we'd like to come up with a systematic way of doing it each time. And also, instead of thinking of it as a single parameter value, think of it as PDFs, which can be carried through the, to the climate projection, thus including uncertainty quantification in our climate projections. So I'm going to stick with MIMA, which is a nice model because it runs fairly quickly. It's got an interactive QBO, et cetera. So here's a little bit more about 8099. 8099 defines for a gravity wave event a spectrum of momentum flux versus phase speed c. So that's what I'm showing you here. And this half width of the phase speed is a parameter that has to be chosen. It is a function of latitude, and I'm going to focus here on the tropics because I've been talking about the QBO. The other parameter that is of interest is this intermittency parameter, epsilon, because gravity wave events are actually quite intermittent, particularly the orographic ones. And 8099 accounts for this through this intermittency factor epsilon. And this has this total gravity wave stress, which I'm going to call BTEC, which is really hard to constrain using observations. So this is another parameter that has to be decided in the 8099 GWP. So for this part of my talk, I'm going to focus on these two parameters, the half width of the spectrum in the tropics and the total gravity wave stress in the tropics. And I'm going to try and calibrate these two parameters to get a realistic QBO. And by a realistic QBO, I'm just going to have two things, the period of the QBO and the amplitude of the QBO. So here's our inverse problem down here. You can think of y as the observable, so that is the output, the period and the amplitude of the QBO, which we would like to optimize. And theta, where's my mouse? Yeah, and theta you can think of as just being two things, the half width of the phase speed that's launched off in the tropics and the total gravity wave stress in the tropics. And you can think of this G here as just being the forward model, so that's MIMA in our case, and you can think of this as just being internal variability. We're going to use this Calibrate-Emulate-Sample approach that was laid out by Cleary et al. In the Journal of Computational Physics back last year. This has been used in Tapio Schneider's group to do some calibration and uncertainty quantification of convector parameterization. I'll talk you through the method on the slide and then talk you through exactly what we're doing in our specific example. The first step here is the calibration, for which we are going to use ensemble Kalman inversion, which is kind of like an ensemble Kalman filter, which is used in data assimilation. What this does is that it minimizes the cost function between the output of your model, so in our case, the period and the amplitude of the QBO, and the truth, which is what we would like it to be. And it updates these parameters at each stage based on minimizing this cost function. And so it pushes us a bit closer at each iteration towards the desired period and the amplitude of the QBO. Once we've done that, doing this sets off an ensemble of integrations at each iteration. And we are going to use this set of input parameter values for the GWP and the output to build a Gaussian process emulator, which is sort of an approximation to a theory. It just gives us, not really an approximation to a theory, it gives us a set of outputs from a set of inputs. And then we can then sample the space using an MCMC method to get a posterior distribution. So let me talk you through exactly what this looks like for our two parameter and two output example. So here is the calibration step, so the ensemble Kalman inversion. At each iteration, we are setting off 10 integrations of MIMA. So we've got lots and lots of forward integrations of NEMA as an example of this. So what we're looking at here is on the top, these parameters, the half width of gravity waves that are launched off in the tropics and the total gravity wave stress again in the tropics. At the bottom are the two things that we are trying to optimize. So the period of the QBO and the amplitude of the QBO. And you can see with each iteration, hopefully we are getting closer and closer to something like the truth. The truth here is just a long integration of NEMA, but then one could use observations, one could use anything one wanted really, but we are just using sort of a perfect model setting to begin with. So you can watch this moving closer and closer towards convergence. It never really converges because it converges at infinity, so we've just got to call it at some point. And so we've generated here with 10 iterations and 10 ensemble members at each point, 200 forward integrations of NEMA, which are still relatively somewhat short. And this method also takes the standard deviation of the period and the amplitude into account. Having done that, we can use some of these integrations to train a Gaussian process emulator, which basically tells you what the period and the amplitude are as a function of these two parameters, the half width in the tropics and the total gravity wave stress in the tropics. So we've trained on 150 samples, and what I'm showing you here is a test against the 30 samples that are left at the end. And this red line here is the one-to-one line. So what this is showing is the period, the truth versus the emulator. And so if the emulator is doing a reasonable job, it means that it should lie along the one-to-one line, and it kind of does. The test works pretty well. Having done that, we can now build these contour plots of what the period and the amplitude look like as a function of these two parameters. So we've got the half width on the x-axis and the total gravity wave stress on the y-axis. So this, if you will, is something like a theory for the QBO as a function of these two parameters, the half width in the tropics and the total gravity wave stress in the tropics. And the Gaussian process emulator carries through a standard deviation. So that's what I'm showing you here at the bottom. Having done this, we can now use an empty type process to sample the region of the phase space where the period and the amplitude are approximately in the neighborhood of what we would like them to be. So that's what this is. This is showing you the path of the MCMC, the standard random walk metropolis. So this is sampling the region of this contour plot. So we've got half width again in the x-axis and the total gravity wave stress on the y-axis. And this is showing you the path of the MCMC as it samples the region of this contour plot where the period is approximately in the range of what we would like it to be. And on the right, where the amplitude of the QBO is approximately in the range of what we would like it to be. If you plot this as a PDF now, this is what I'm showing you here, and the conditional probability distribution. This is the half width in the tropics and the total gravity wave stress in the tropics. The blue is the prior distribution. I should have mentioned it's a log normal distribution because we need both of these to be positive. The green is the truth that we are trying to calibrate to, and the blue is the posterior PDF. You can see that that this PDF sort of looks like what Laura and I have been calling a banana distribution because it looks kind of like a banana. You can see that the total gravity wave stress in the posterior here has been narrowed quite a bit. So there's actually quite a narrow distribution of total gravity wave stress, which gives you a meaningful QBO. Whereas you have a pretty wide range of half width of gravity waves in the tropics that gives you a reasonable QBO. So the posterior in the case of the half width in the tropics hasn't actually been narrowed all that much. Now we can sample from this posterior distribution and actually get a parametric uncertainty associated with changes in the QBO. So what I'm showing you here is kind of that. And to cut a long story short, basically in the parametric uncertainty associated with the QBO is sort of equivalent to the internal variability in the model. So it's actually reasonably significant. This is Laura Mansfield who did all of the work, and the work is revision at James. I'm hoping it should be accepted soon. Again, this is another method which we've presented using a long run of the model itself, but then you could calibrate and do uncertainty quantification based on any truths that you like, including gravity wave resolving simulations. You could use observations. Talking of observations, I have 10 minutes left, right, Dominic?
Yeah, 13, and then maybe sort of a few minutes for questions. Yeah.
Oh, okay. So I'll tell you a little bit about Project Loon, and then tell you a little bit about where all of this is going in the future. So I don't know how familiar people are with Loon. I sort of ask for a show of hands typically when I talk about it. But Project Loon came out of Google X, which I think is just called X now, and they have launched thousands of balloon flights. They started off in 2014 from New Zealand, and more recently they've been launching from Reno, Nevada, and from San Juan in Puerto Rico. And their idea in putting these super pressure balloons into the upper atmosphere was to provide internet to everyone below it. They shut down in 2021. But before they did that, we acquired between 2013 and 2021 thousands of balloon flights. This is not a scientific ballooning campaign. They just happen to have GPS on board. And so they happen to measure the latitude, longitude, height, temperature, and pressure. About every 60 seconds, some of these observations are even more frequent than 60 seconds. So despite its flaws, it's a really valuable new data set. And rather well suited to be looking at gravity wave statistics in the upper atmosphere, which came in really useful when I started thinking about gravity waves. This is a plot from my postdoc Eric Lindgren's first paper on this data set. This is back in 2020. What I'm showing you here is color-coded by month, going from January through to December. And what you can see is that it's not quite global coverage, but it's actually pretty good. There's no coverage over much of Western Europe and Asia because Russia, China, and India, I think, wouldn't have these balloons in their airspace. But it's pretty good coverage over the Southern Ocean because they were launching from New Zealand. And it's actually pretty good coverage over the tropics to look at the QBO region and things like that. Compared with a typical scientific ballooning campaign, which is of the order of a dozen balloons or so, the data from those dozen balloons are obviously very much better than the data that we have from these, but this is thousands of balloon flights. Eric's paper consisted of spectra and things like that, and how they vary through the seasons and the latitudes and so on. But Brian Green, who is a postdoc in my group at the present moment, has developed a pretty nice, sophisticated wavelet code, which we are hoping can be used to look at actual gravity wave packets. What I'm showing you here on the left is the directional gravity wave momentum fluxes estimated from these thousands of balloon flights. This took a lot of patience because, as I've said, this is not a scientific ballooning campaign. The sensors cut out. There's sometimes maneuvering, so these balloons are moved up and down, and we don't necessarily know when they're being moved up and down. And to follow gravity waves, we would like them to be as close to passive tracers as possible. But at the end of a lot of analysis, this is zonal momentum flux on the top. This is the mean, and the y direction at the bottom. Some features are quite evident, like you can see orography. You can really see the Andes in the zonal momentum fluxes. These are the mean values. Brian is working on writing the stuff up. On the right is the variability. The variability is quite interesting. This is over the Indian Ocean specifically, and you can see that the 99th percentile really has a contribution. He's also been doing things like breaking this down sort of into orographic and non-orographic gravity waves just by applying a mask on the orography. These are PDFs of the total momentum fluxes from the orographic in the red, I think, and the non-orographic in the blue. These are log normal distributions, which is consistent from previous ballooning missions, for instance, from the French Space Agency. The non-orographic distribution has a longer tail than we would have expected. However, we don't really have data from the same position. This is pretty much over the westerly jet over the Southern Ocean. from which we don't really have previous data, but then the non-orographic distribution does seem to have a longer tail than we would have expected. We are working on putting up the wavelet code as well as the flights themselves, not to mention the fluxes and other spectra. Some of it is up already on a data portal from Stanford, and we would be very happy to share any of this data with anyone who's interested, because it's been a tremendous amount of work. And if there are other ways in which this could be of use, I think that would make us very happy. But ultimately, the point is to be able to train both the gravity wave parameterization as well as the calibration on something like observations. But also, we're working with these very high resolution simulations, both global as well as regional, and I'll just introduce them very, very briefly. This is a snapshot of drag, so zonal drag at the top and V drag at the bottom. This is from 1.5 kilometer simulations of the ICON model. So this is the icosahedral non-hydrostatic model from the MPI. These were run by Laura Kohler and Claudia Stefan at the MPI. I'm showing you a region in the Southern Ocean, and you can see that there's some really nice fine scale structure involved in this. And we need to figure out how to use these very high resolution, pretty much, it resolves much of the spectrum, not all the spectrum, of course, but how can we use this drag in both approaches, both the machine learning approach as well as the calibration approach? And I'll show you some of the challenges associated with this. And what I'm showing you here is gravity wave drag from ICON, which is this very high resolution model, in the black, and MIMA, which is our climate model that we've been playing with, in red. This is in the crucial equatorial region where the drag pretty much sets up the QBO. And you can see that MIMA pretty much underestimates the drag in the QBO region. And so we are working on trying to figure out how to generalize both approaches that I've showed you to include these high resolution simulations. The high resolution simulations are of necessity kind of short, so we only have a week every month. And we picked a year in which we have pretty good Loon coverage, and so we are hoping to incorporate both the observations as well as the high resolution simulations to learn from both of these and put them back into a coarse resolution model. So more on that to come. Hopefully, maybe you can invite me back in a year and I can tell you about that. So let me just introduce DataWave, which is a project that we are all working on, and tell you a little bit about the people involved in it. And then I'll be very happy to take questions. So DataWave is focused on improving both our understanding and our representation of atmospheric gravity waves. These are all the PIs. Ulrich Katz and Claudia Stefan are in Germany. You've seen some of Claudia's work. They're doing these very high resolution simulations. Ulrich is working on retracing to actually attempt to follow gravity wave packets around. As you can imagine, it's computationally expensive, but we're attempting to figure out how we can do something similar to that without the computational expense. Ed Gerber and Pedram Hassanzadeh are both based in the US, as well as Joan Alexander. Joan is an absolute expert at gravity waves, and Ed and Pedram, like me, are climate modelers and sort of large-scale aerodynamics people. Adam Scaife at the Met Office, they've also been developing a machine learning gravity wave parameterization, which now I believe is coupled back into their model. So that's nice. And I think I haven't mentioned Francois Lott, who's at the LMD. They have a great deal of experience with scientific ballooning campaigns and have been very helpful on that front. And they also have access to the IPSL model, which is interesting. So yeah, it's too bad I couldn't see anyone's faces when I was talking, but I'm very happy to take any questions, and thanks so much for your attention.
So if we switch to this, you can see some of the audience. Can you see us?
Yep, kind of.
And there's also a way that you could, yeah. Oh.
Yeah, look at that.
I don't know, but that was exciting. No, wrong one.
There we go again.
Check. Composite you on that. Okay.
Thanks for the nice activity. So basically I do have a question in terms of the forcing from wave breaking. Because basically that paper you talk about and your work is important how the wave breaking versus the horizontal movements. Do you have a rough idea of how the wave breaking will impact the vertical?
I'm sorry, I didn't quite hear that. Do I have a rough idea of how the wave breaking will impact what?
Vertical velocity.
The vertical velocity. Do I have a rough idea? Yes, we kind of have a rough idea. Yes. I mean, are you talking about the ML bit or the calibration bit? Sorry, I just didn't hear you.
Oh, I'm sorry. So basically, I'm not asking about the calibration part. I'm more like interested in terms of the variable wave parameterization itself. So when we're talking about the forcing of the wave breaking events to the momentum. So those parameterization usually applied it onto the horizontal.
Or the horizontal, right? Yeah.
Yeah, so I'm just curious about how it impacts the vertical velocity.
Ah, I see. Okay, that's a good question. I don't think so. Okay, so we make the assumption that vertical velocities are kind of small, right? In the context of large scale dynamics, anyway. Of course, that's probably not true in convection. That's a good question. I don't know.
Okay, maybe we could discuss offline.
Yeah.
We were sort of like one of implements similar, but in like a non-static model. So
Right. Yeah. So from Icon, I think that again, I didn't quite hear you, but if you're talking about the high resolution non-hydrostatic, I think there would be sort of localized cases in which there's probably quite a significant effect. That's a good point.
thank you.